Okay, so in this video, we will discuss the zero matrix. As we will see, it's a very simple matrix, and its role is to play the same role as the zero real number when dealing with real numbers. Let's look at two very simple examples. Suppose I let matrix A be a 2 by 2 matrix. Let's go with 1, 3, negative 2, 5. And what if I compute A minus A? So I do A minus A. Well, 1, 3, negative 2, 5 minus itself, 1, 3, negative 2, 5. When we subtract matrices, we subtract corresponding entries. So this will still be a 2 by 2 matrix. But since all corresponding entries are the same, every entry of the subtraction will be equal to 0. And so what we have is a matrix where every single entry is 0, and we call this the zero matrix. Now we can write this in two ways. We can write 0, so an uppercase 0, and we can specify the size, which is a 2 by 2 zero matrix. But usually we don't write the size because implicitly, whatever the size of A is, the matrix 0 will be of the same size. So we can simply write 0. So if you ever have matrix A minus itself, you can simply write this as equal to 0. We understand here that this is a matrix where every single entry is equal to 0, and the size of this matrix is the same as the size of A. Now the matrix A doesn't have to be square, right? You could look at a second example. Let's take a, say, 3 by 2 matrix. And once again, if we compute A minus A, when we subtract matrices, we subtract corresponding entries as they are all the same. We get once again a matrix where every single entry is equal to 0. So we could write this again in two ways. We could write this as an uppercase 0, and we could specify explicitly the size, 3 by 2, 3 rows by 2 columns. But again, this is not necessary, as whatever the size of A is, this will be the same size for our 0 matrix. So we simply write uppercase 0. And that's the 0 matrix. And again, the nice thing about this matrix is it behaves algebraically just as the 0 real number. Let's look at the basic properties of the 0 matrix to see that it really behaves like the 0 real number. Well, the first property we've already seen. If we do A minus A, where A is any matrix, we get a matrix of the same size that consists of all zeros, and we simply write uppercase 0. So A minus A is the 0 matrix. You could ask, well, okay, what if I do A plus the 0 matrix? Here again, implicitly, the size of this matrix is the same as the size of A, so the addition is defined. And if you think of it, if you add to a matrix the 0 matrix, this means you add to every entry of A 0. So nothing changes. You get back the matrix A. And the same thing goes in the other direction. If you do 0 plus A, once again you get A back, just as you would if 0 and A were real numbers and not matrices. One last property. What if you have square matrices of the same size in 0 and A, and you multiply them together, right? If lowercase a was a real number, then lowercase a times the 0 real number equals 0, and 0 times the real number also equals 0. Well, this is also true of matrices. So if A and 0 are both square of the same size, so they're both n by n matrices, A times 0 will be equal to the 0 matrix. It will still be an n by n matrix, and 0 times A will also be equal to the 0n by n matrix. And so you see quite simply, when you handle matrices algebraically, you can use the 0 matrix as you would the 0 real number. Let's just check this quickly and you'll see that again this is fairly obvious. Let's take, say, just 2 by 2 matrices. So suppose A was 1, 2, 3, negative 4. And here again 0 will inherit the same size as A. So it will be the 0, 2 by 2 matrix. And if you do A times 0, this is a 2 by 2. This is a 2 by 2. The result is also a 2 by 2. And it's going to be obvious that every entry of A times 0 is 0. Because when you multiply a row times a column of zeros, you're adding zeros. And so this is just obvious. The other direction is equally obvious. If you multiply 0 times A, now you do a row of zeros times a column. Whatever the entries in the column of A are, if you multiply them by a row of zeros, you're adding zeros. And so every entry is just 0. So in both cases, A times 0 is 0. 0 times A is 0. And that's it. So you can write 0 when you do algebra on matrices. And the implication is that this is the 0 matrix, and it has the same size as the other matrices. And that's it.